understand the standard charging circuit that we're basically evolving from this circuit at the very beginning to this circuit at the very end. Because as the capacitor charges, it becomes more and more doesn't want to take anything else. This is also going to be our only mechanism for understanding what I'll call non-standard circuits. Okay? So far we've talked about standard circuits. And our standard circuits are basically this. There's our standard charging, and here's our standard discharging. So one is charging a capacitor from a battery, and one is then letting it discharge through. Those are what we call our standard circuits. Now, you can have quite a bit of flexibility. For instance, if you're charging a circuit, you don't have to charge it through just one resistor. Maybe you're charging it through a bank of resistors. And maybe you're not just charging one capacitor, maybe you're charging a whole bank of them. We'll take a look at combining capacitors in series and parallel as well. And same thing over on this side. Maybe you're not discharging through just one resistor, maybe you're discharging through a whole bunch of them. And maybe it's not just from one cap, but maybe a whole bunch of them. Yes. Yes. So a whole bunch of stuff can be combined into an equivalent resistance or capacitance. So there are things, however, that will not play nice with either of these. In both of these, you would get the tau as by multiplying the equivalent resistance times the equivalent capacitance. So the resistor or resistors that you're trying to discharge or charge through, and then the capacitor or multiple capacitors that you're trying to discharge or charge with. But these equations clearly cannot apply because this right here means that the current eventually goes to zero. Okay? So our whole premise was that at some point the current's going to go to zero either because you're done filling your capacitor or you're done emptying it. There are circuits where, as an immediate red flag, you notice they are non-standard. Because the current will never go to zero. So right away you know that your functions cannot possibly apply. Here's an example. This is a non-standard circuit. So how do you know it's a non-standard circuit? Well, you can look at that and say, even when that capacitor is full, that capacitor is actually in parallel with the resistor, which means that even if you can't go onto the cap branch, there's another way around that will never stop flowing. So this total current in this circuit will never go to zero. Even when the capacitor is full, there's still another way around. So what do you do in these circuits? Well, your scope is greatly limited. You don't have the time equations. I'm only giving you the time equations for these standard circuits. Got to cut off the level of complication somewhere. So the only things that I expect you to be able to manage the time equations is the standard circuits. You do not have the time equation for this. So what do? I cannot ask you in these circuits, what is the going on at time equals 7 seconds or something like that, because you don't have the equations. I can ask you about 2 times. What's going on at t equals 0, and what's going on at t equals infinity. So what do? At t equals 0, if the cap is empty, you effectively replace that cap with a short circuit and analyze what all the flows would be with the short circuit in place of the cap. What do you do for t equals infinity? You essentially replace the cap, which is now full, with an open circuit, and then analyze the circuit accordingly. So these are nice problems. I think I like to give them. I believe there's at least one of them on the practice exam, because it basically gives me the ability to give you a circuit and have a 2-for-1 deal. Because it's basically two different circuits. It's one circuit at t equals 0 when the capacitor is acting like a short, and it's another circuit at t equals infinity when the capacitor is acting like an open circuit. So I can ask you to do all your normal circuit analysis, but instead of just having the fun of a single battery with resistors, it looks like one circuit at the beginning and one circuit at the very end. So I can ask you for all the currents and voltages and stuff twice. So that's a vital skill, right? So if you shouldn't be able to do one of these deals, a bunch of the stuff that you did on homework number 3, right? That connects the middle of the resistor. That's weird, right? So that's bread and butter stuff. You should be able to walk into the exam and be able to take a single battery plus however many resistors circuit and be able to calculate what are the current and voltages across every element. That's just bread and butter stuff, okay? So what I do is I'll throw in somewhere a capacitor. That allows me to basically give you two circuits. It's one circuit, it's behaving one way at the beginning when the capacitor is empty. It's behaving this other way when the capacitor is full, okay? Are there any questions on this? Okay, so you do have one of these on your homework. I wish there were more, but you'll see it all over the practice exam. So that's obviously giving you 3 of them is going to give you more of an idea of the kind of things that I tend to like to ask. Okay. Okay, so that's it for RC circuits. Are there any questions on that before I change gears completely? Okay, so next order of business, dielectrics. Going to leave the real basics up there, but clear off all this particular circuit. So, dielectrics. Dielectric is a way to soup up the performance of the capacitor. If the capacitor is not performing, it's not as good of a storage device as you like, you can improve it. You can improve it with altering its physical construction. Remember we said that the capacitance depends on the physical construction? Well, let's mess around with the physical construction. I'm not going to mess with the area or the plate separation. I'm going to put some stuff into the space between the plates. So it's like an ice cream sandwich. I'm going to put in the ice cream. Okay? So I'm going to have my 2 capacitor plates. Remember, those are 2 conducting plates. And I'm going to throw in between, filling the entire space between them, a material. So that's called the dielectric. Now first things first, if I have plus Q here and minus Q here, the last thing I would want is that piece of material to be a conductor, because that would just allow the plus to flow and cancel off the minus, and I'd have a big neutral hunk of stuff, right? So clearly whatever this red stuff is, the filling, can't be a conductor. In fact, it's an insulator. In fact, dielectric is just another word for an insulator. You'll hear some people just say one word or the other all the time. I use the word dielectric when I'm repurposing an insulator for this particular purpose, but dielectric itself is just another word for insulator. So you might say, well, how would that possibly improve the performance of this thing to just have a hunk of insulator in between? So I'm going to walk you through how that works. Now let me remind you, for instance, if we had an electric field and we had a hunk of insulator in there, it does charge polarize. So minus, 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 plus, plus, plus. Not as much as the conductor, right? We found that the conductor, the only reason it stops charge polarizing is because it's already canceled off the entirety of the electric field in the interior. So it just basically means that the whatever electrons are in the body of the interior have no more desire to polarize. So this was the idea of perfect shielding. It's why being in your car during a lightning storm is a good idea. Dr. Megavolt, if you watch those videos, he's still alive because of perfect shielding. But this is not a conductor, it's an insulator. So let me remind you what we learned about insulators, this idea of partial shielding. So the net electric field inside is less than the external, but it's not zero. And the reason why we learned that insulators are not able to perfectly shield here is because you're inherently limited with the amount of charge carriers that are available. You are not having a bunch of totally free electrons ready to flow wherever they please. You are limited basically into atomic reorientation. These are really kind of the negative end of atoms that have rotated, and these likewise. Those are bound charges. Those still belong to the particular nuclei that they were before. They've just reoriented. That's what I'm going to have here. These plates cause an electric field, which of course points from here to here. I'm going to call that E external, because of course that's external to the dielectric material. And you're going to have charge polarization of this material, like so. And that's going to create an E induced. That points like this. Of course, this is throughout the region. But I don't want to draw it everywhere because I need space to do the labels. But basically, if you want to do the vector sum, it looks like this. You have E external from the plates themselves. You have E induced from the dielectric. And the net field, if you want to add those two, looks something like this. So E net is smaller than E external, but still in the same direction. So it basically just took the edge off a little bit, right? We have partial shielding. Now that part is hopefully all review. We talked about all of that stuff in the second homework. And I even hinted to you at the time that you might, seeing the point of perfect shielding and its applicability is pretty obvious, right? Safety and all that stuff. But partial shielding didn't really seem to have a point, right? If you take a little bit of the edge off, if E net is slightly smaller than the external, if that's the slightly smaller going to kill you electric field, that's a small consolation. So we don't want to count on this for protection. E net can be still substantial on its own, even if it's smaller than E external alone. So what I want to now do is walk you through the logic of how this actually improves the performance of a capacitor. That much is not clear perhaps yet at all. So how is it that this partial shielding translates to why is it performing better? So let's go through that. So I want to go ahead and make myself a nice chart here. So my initial point is going to be a fully charged cap. So I know that's an odd initial point because we said that it takes forever to do that. But let's say we've charged the capacitor up to full, and then what we can do is talk about what values that it has initially. So let's say, I don't know, we'll call it Q naught. That's the amount of charge that's on each plate. Let's talk about the capacitance itself. Let's talk about the voltage across the capacitance. Let's talk about the electric field. Net, I guess. Actually, let's call it just E naught. Let's talk about the potential energy that's stored. And we're going to see how all of these things evolve as we start now messing with a dielectric. We put in a dielectric. So let's now insert the dielectric on the assumption that the cap has been removed from the charging circuit. So let's say cap by itself, just like I've drawn it. All right. So we're going to see how all these different properties evolve. That VC now looks ugly to me, so I'm going to go like this. I'm going to go, this is the voltage across the cap. There's going to be no resistors involved, really, so I don't think that'll be that confusing. And then this, I'm going to have be the net electric field, okay? Okay. So we charge this thing up. We get plus Q naught and minus Q naught, one on each plate, and now we insert the dielectric. So first of all, the amount of charge that's accessible and available stored on each plate, how is that affected by inserting the dielectric? Can we count this negative and this positive? Can we count that as just stuff we can have flow off for use? No, it's bound, right? Remember, it's just the butt ends of these atoms on the material. So we can't have access to that. So what happens to the amount of accessible charge? Charge is stored on the capacitor. It's exactly the same. So it's the same. So the moment we disconnect the capacitor from its charging circuit, we have these isolated islands of charge. There's nowhere for the charge to come off of or to go or to come from. And all we've done is take a neutral hunk of insulator and put in between. So there's no change to the charge. I guess let's jump down to the electric field. What happened to the net electric field between the plates? So we went from just this to this, right? When we insert the dielectric, we get that partial shielding, right? So this should decrease. Partial shielding, right? Now, we need a way to quantify that. We only talked about it conceptually before, right? We only talked about it in terms of it's reduced. We never said, here's how we might quantify the number, right? So let me tell you how we quantify that reduction. So if this is less, here's how we do it. We come up with a property of this material. This material is going to have a thing called kappa associated with it. And kappa is called the dielectric constant. So kappa is the dielectric constant of the material. It's different for different materials. And here is how it's defined. Now you might say, if E net here is basically going to be E external minus E induced, right? That's how you would actually get that. So you might say, couldn't we just quantify E induced and talk about how much we take away and think of it as like a subtractive thing? Well, for reasons that I will get into later, we don't want to just quantify it as a, here's how much you subtract. We want to talk about it as a divider. So the kappa constant for a material is how much you have to divide the field that you would otherwise have to get to the net field. So for instance, kappa equals 1 for a vacuum. Of course, if there's absolutely nothing there, then there's no partial shielding to be had. But kappa is greater than 1 for all materials. All materials have some capability of doing this. So as an example, if a material had a kappa of 3, you'd find that's pretty good, because your net electric field inside is only 1/3 of what it would be. You're shielding off 2/3 of the external field and only have 1/3 left. Right? If your kappa was 4, kappa of 4 would mean that your net electric field inside is only 1/4 of the external. So you're taking off 3/4 of it and only leaving 1/4. You can have materials that have kappa values of 1,000. So that means that's pretty good shielding, right? If your net electric field inside is at 1,000th of what it would be otherwise. So that's how we quantify that shielding, is as a divider. Okay? It's better that way. It's sort of like a percentage, except for it's in the denominator. So instead of having to talk about half or 1/3 or 1/4, it allows us to just talk about the 2, the 3, and the 4, right? So it turns out that's a better way to do this, and I'll talk about why we want to talk about it as basically a division instead of a subtraction. So let's go and put it over here. We know that partial shielding is going to reduce the electric field that we would otherwise have. The net field will now be 1/kappa times the previous one. So now that we've got that out of the way, how we're going to quantify our partial shielding, we can actually go ahead here and see how that trickles down to everything else. So let's take a look at the relationship between electric field and voltage. This is something we talked about in on the second homework. Yeah, second homework. So the electric field talks about how rapidly the voltage changes with distance, right? Electric field always points towards lower voltage. And the more precipitous that plunge in voltage is, the more the electric field will be. Now, this right here looks a bit awkward. First of all, the voltage changes, of course, happening from one plate to the other. We've been calling the plate separation D, so we should call this V. And then we haven't called it delta V for several homeworks now. We've called that V. So E equals V over D. So that is the relationship. And since we're not actually changing the separation of the plates at all, D is fixed, what it tells us is that there's a direct proportionality between the strength of the electric field and the voltage drop. So if the electric field gets reduced between the plates, the voltage drop will be reduced between the plates. So we can go over here. What's the voltage drop between the plates? That's also gotten reduced by the same factor. We've reduced the voltage difference between the plates. Okay? So, how can we reason this? Well, let's take a look. We had this positive charge that we put on the plates, negative charge that we put on the plates. Let's say we charge this up with a, I don't know, what do you want, 9-volt battery, right? I like 9-volt batteries. Both terminals are next to each other, okay? So if we had charged this up and the initial voltage was 9 volts, right? And let's say, for example, we stick in a dielectric constant of 2. What that means is that now the voltage difference, 9 divided by 2, is 4.5. The voltage drop is now 4.5. The charges just aren't as excited to go across. So for instance, if we wanted to discharge this capacitor, right?